Welcome back to the AI and Automation Masterclass. Today, we're stepping right into the dark obsidian cyber laboratory of real-time automations. In this explainer, we're unpacking a concept that is literally the backbone of modern, event-driven architecture, webhooks. You know, if you've ever wondered how on earth disparate applications communicate instantly without absolutely crushing your servers, or how those autonomous AI agents know exactly when to wake up the very millisecond new data arrives, well, you are definitely in the right place. Let's get right into it. Okay, let's dive into this masterclass syllabus. First up, polling versus push architecture. Then we'll map out the webhook lifecycle. After that, cryptographic security and verification, followed by error handling and resilience, and we'll wrap it all up with the enterprise AI pipeline.
All right, section 1, polling versus push architecture. Or as I like to call it, the don't call us, we'll call you paradigm.
So we really need to address the core conflict in API design first. Think of traditional REST API polling like that hyperactive kid in the backseat of a car just constantly asking, "Are we there yet? Are we there yet?" Your client application is sitting there repeatedly querying a server on a scheduled timer, maybe every 15 minutes or so, asking, "Hey, is there new data?" And well, most of the time the answer is just no. It's a massive inefficiency. You're burning through API quotas, experiencing high network latency, and just completely wasting your compute cycles. But webhooks are a total game changer. They use a push-based mechanism. It's like that instantaneous GPS notification that just pings you the moment you actually arrive. Zero idle overhead. The second a source application detects a state change, like say a brand new Stripe payment or a GitHub code push, it immediately formats that data into an HTTP post payload, usually JSON, and just pushes it directly to your destination.
And look, when we say instant, we mean absolutely instant. We're talking about latency of less than 100 milliseconds, literally a fraction of a second. By shifting to this push-based architecture, you are finally ditching those wasteful 15-minute polling timers and stepping into the realm of true real-time orchestration. Honestly, this is absolutely crucial. It's the only real way to build highly responsive autonomous AI systems.
Moving on to section 2, the webhook lifecycle. We're tracing the JSON payload's path.
Let's actually trace the path of our JSON payload through 3 distinct mechanical steps. Think of it like passing through physical security gates in our cyber lab. Gate number 1 is registration and handshake. Your destination endpoint provides a static URL listener, so think of a make.com or an N8N URL. The source system registers this listener and securely binds it to an explicit event trigger. Gate number 2 is the transmission. The source detects that state change we just talked about and fires the HTTP post request packed with that JSON body. And then we hit gate 3, the response, which is highly critical. The destination server has to process that payload and fire back an explicit HTTP 200 OK success status code immediately. If you don't acknowledge that receipt right away, the source system is going to think the delivery failed, and that can trigger automatic retries or worse, get your webhook disconnected entirely.
Now, what's genuinely fascinating about this setup is how enterprise orchestration tools actually handle these endpoints in practice. Let's take N8N as a real-world example. They actually generate 2 completely separate URLs for your workflows. You've got your test URL, which is super useful for building and debugging because it listens for just 120 seconds and visually renders the incoming payload data right there in your editor UI. But once your pipeline is actually live, you switch over to the production URL. This one listens continuously until you unpublish it, but it entirely skips that UI rendering step just to maximize performance. You absolutely must know which gate your data is flowing through when you're deploying these pipelines.
All right, section 3, cryptographic security and verification, protecting the Cyberlab gates.
So we've talked a lot about speed, right? But exposing these automated orchestration systems to the open internet is frankly incredibly dangerous. Here's the terrifying reality. If you've got a public URL that triggers an expensive AI workflow or say modifies a production database, well, anyone with that URL can just send an HTTP post request to it. So how do you actually know who is knocking on your webhook URL? How can you be sure the request is genuinely from GitHub or Stripe and not just some malicious actor trying to brute force prompt injections into your AI agents?
Well, that brings us to HMAC, or hash-based message authentication code. It is an absolutely essential cryptographic handshake. Here's how it works. When a legitimate provider sends a webhook, they take the raw payload data and a secret key, a key that only the two of you share, and they run it all through a cryptographic hash function, typically something like SHA-256. They then attach that resulting hash right into the HTTP header. When your server receives it, it basically does the exact same math. If the hashes match up perfectly, you know mathematically for sure that the sender holds the secret key and that the payload hasn't been tampered with while it was in transit. It's brilliant.
To really lock things down, robust systems like NROC or custom node servers rely on a multi-layered security framework to mitigate those vulnerabilities. First up, we have the HMAC SHA-256 signatures we just broke down. Second is IP whitelisting. This is just validating that the incoming traffic originates exclusively from trusted subnets that are actually associated with your webhook provider. Third, we enforce strict course policies and payload sanitization. This is huge for stopping cross-site scripting vectors dead in their tracks. And fourth, replay prevention. By checking something called the timestamp tolerance, your system can actually reject a valid but intercepted webhook payload if an attacker tries to resend it a few hours later.
So the crucial point is this: your webhook listener has to be ruthless. I mean it. If a signature fails validation or an IP doesn't match the whitelist, you do not pass that data downstream. Period. You terminate the request immediately and return a 403 forbidden response. Doing this is literally the only way to safeguard your database and protect those sensitive downstream AI processing layers.
Moving into Section 4, Error Handling and Resilience. Engineering for Failure.
You know, in distributed systems, failure isn't just a possibility, it's an absolute certainty. Let's map out how we build true resilient enterprise architecture. If you're dealing with temporary network degradation or a 5x server error, the standard fix is exponential backoff and retries, which you configure over on the source side. But wait, what if a retry causes a duplicate send? To prevent absolute disasters, like say double billing a customer in a payment automation, you have to use item potency keys. These are usually UUIDs attached directly to the payload, allowing your system to quickly check if it's already processed that specific transaction. And finally, for unparsable or corrupted payloads, you route those straight to a dead letter queue for later debugging, rather than letting them jam up or crash your main production listener. You also have to keep real-world infrastructure constraints in mind. For example, if you're using NN Cloud, they use Cloudflare for protection, right? Well, Cloudflare has a very strict 100-second timeout limit. So if your downstream AI process takes, say, 3 minutes to generate a complex answer, Cloudflare is just going to cut the connection and hit you with a 524 status code. To get around this, you have to split your architecture. You use one webhook to instantly acknowledge receipt, and then a totally separate second webhook to deliver the final result once that long-running AI process actually finishes.
Let's head into our final stretch, Section 5, the Enterprise AI Pipeline, Node.js, Express, and Agentic Routing. Let's bring all this theory together into code and construct an instantaneous webhook listener using Node.js and Express. We can trace our payload's lightning-fast journey step by step. At 0 milliseconds, our Express server intercepts that JSON payload. Boom! By 10 milliseconds, our custom middleware is already running the HMAC verification. At 20 milliseconds, Node's built-in crypto module uses timing safe equal to securely validate the digest, which prevents any sneaky timing attacks. By 30 milliseconds, we've already fired back that crucial 200 OK response to acknowledge the source. And finally, at exactly 40 milliseconds, our system triggers the asynchronous AI agent pipeline. Total elapsed time? Literally less than the blink of an eye.
And this brilliantly illustrates the exact mechanism in Node.js. Using that native crypto module, you simply call create HMAC, pass in your algorithm, like SHA-256, and drop in your secure environment variable, your webhook secret. You then just update this object with the raw body buffer of the incoming request. Honestly, it's elegant, it's native to Node, and it guarantees that your application only ever processes cryptographically verified, safe data.
To summarize this explainer today, we are witnessing a massive fundamental paradigm shift. We are officially moving away from the wasteful, compute-heavy dark ages of API polling and stepping fully into a dynamic, push-based architecture. Webhooks are quite literally the nervous system of modern applications. They're the instant callbacks that allow all your disparate tools to act as a single, cohesive, millisecond latency machine.
So, I'll leave you with this final thought to help you evaluate your own systems. Look really closely at your current infrastructure. Are your automations still sitting on a 15-minute timer, just endlessly asking the server if there's anything new to do? Or are they utilizing webhooks to instantly react to the world the very second an event occurs? It might just be time to upgrade your ecosystem. Thanks for focusing in, and I'll see you in the next explainer.